So here's an example where we have three charges in an equilateral triangle. We'd like to find the net force on the charge on the top. I'm going to take you through the steps on this one because sometimes people get a little bit confused when we're talking about electric forces. So think back to physics 1050 or 1020. If we had any object with multiple forces on it, how would we solve that problem? Well, we'd have one step where we drew the free body diagram. And then our next step would be to find the components of the forces. And then our next step would be to do a vector addition. F net x is the sum of the x components, and F net y would be the sum of the y components, and then you would write your answer as a vector. So these problems follow the same steps. We just have one extra step in the middle. In physics 1050 and in physics 1020, we were pretty often given the magnitudes of the forces in our free body diagram. Pretty often we knew what those forces were. In these electric problems, pretty often we don't know the magnitudes of the forces, but we do know the charges and the distances. So we put one step in the middle. We find the magnitudes of the forces. Oh my goodness, quite a day when I can't spell magnitude. Try that again. Where this is a new topic, students do sometimes get confused about how to find the magnitudes of the forces. There is only one correct way to find the magnitude of the forces, and that's Coulomb's law. F equals K Q1 Q2 over R squared. Okay, so let's keep all that in mind and let's get started on the process. So let's get started on the process. Step one, draw a free body diagram. So to make it a little simpler with my notation, I'm going to label my forces Q1, Q2, and Q3. So my top charge I'll call Q1, my lower left charge I'll call Q2, and my lower right charge I'll call Q3. All right, I want to draw my forces on Q1, so that part is already important and we went through that in the lectures. I'm drawing my free body diagram on Q1. So all arrows must be on Q1. If you draw them anywhere else, that's the wrong place and you won't get points for your answer. So let's do the force between Q1 and Q2 first. Those are both positive charges. Therefore, Q1 must be repelled by Q2, so the force on it must be away. So that would be up and to the right. So there's the force by Q2 on Q1. I'm a little bit lazy, so I'm not going to write the word on anymore. So there's the force because of charge 2 on charge 1. So that's our first force. Okay, now let's do 1 and 3 next. So these forces are attractive, so Q1 is going to be pulled towards Q3, so that force is going to be down and right. I'm going to draw that one in a different color. Thinking ahead, I see that Q2 and Q3 have the same magnitude of charge, so I think these vectors are going to be the same length. I'm going to draw them approximately the same length. So that's the force of charge 3 on charge 1. Okay, so that's the first part done. My free body diagram is drawn. If you wish in this step, you can go ahead and draw in your components. That may be useful. So there's the x component of 2 on 1. There's the y component of 2 on 1. So 2, 1x, f 2, 1y. For the y, x and y components of 3, 1. So there's 3, 1x, and there's 3, 1y. All right, so I've drawn my free body diagram, I've got my components. Now I have to go to my next step and I have to find the magnitudes of those forces. So now our next step is to find the magnitudes of the forces using Coulomb's law. So using Coulomb's law to find the magnitudes, let's do force of 2 on 1 first. So the magnitude of force charge 2 on charge 1 is K times the magnitude of charge 1 times the magnitude of charge 2 divided by the distance between 1 and 2 squared. The distance between 1 and 2 is labeled as d in our equation. So that's going to be K. The magnitude of charge 1 is little q. I'm going to write it in symbols first. The magnitude of charge 2 is big Q. And the distance between the two charges that you could label R12 is the distance d, which is 1 millimeter. Okay, we'll put in the numbers next. 8.99 times 10 to the 9 newtons meters squared over coulombs squared times little q, 0.5. That Greek letter mu, that means times 10 to the minus 6 coulombs. And then big Q, 1 times 10 to the minus 6 coulombs. That's called a microcoulomb, where micro is times 10 to the minus 6. Our distance is 1 millimeter, so 1.00 times 10 to the minus 3 meters. That's all got to be squared. Run that through the calculator, you should get 4,495 newtons. Okay, so this is the magnitude of the force. So in physics 1020 or 1050, you might have even labeled this in your diagram 4,495 newtons. Okay, let's find the magnitude of charge 3 on charge 1. So F3 on 1 is equal to K times the magnitude of 1 times the magnitude of 3 times the distance between 1 and 3 squared. That's also the length of our triangle. So that was just d. So that's K times little q times a positive big Q divided by distance squared. Remember, we always use the magnitude of the charges because we're finding the magnitude or the size of the force. 8.99 times 10 to the 9 newtons meters squared over coulombs squared times 0.5 times 10 to the minus 6 coulombs times 1 times 10 to the minus 6 coulombs divided by 1 millimeter squared, or 1 times 10 to the minus 3 meters squared, gives us, no surprises here, 4,495 newtons. And if you wanted to, in physics 1020 or 1050, you probably even labeled that in your diagram, 4,495 newtons. Okay, now we have the magnitudes of the forces. Our next step in our process is to find the components of the forces. Okay, next step, we have to find the components. So from here on out, it's just like doing a physics 1020, 1050 problem. The only special step we have to do in electric charge problems is we have to find the magnitudes of the forces using Coulomb's law. Okay, to find our components, let's do the components of F21 first. So we notice that this is an equilateral triangle. That means every angle in the triangle is 60 degrees. So if that angle is 60, this angle is also 60. So F21x equals the magnitude of F21 times cosine of 60 degrees. If we take positive x to the right, positive y to be up, our x component is positive. So we have 4,495 newtons times cosine 60 degrees gives us an x component of 2,247.5 newtons. For our y component, it's opposite the angle, so we'll use sine. It points up, so it's positive. So we have plus F21 times sine 60 degrees, 4,495 newtons times sine 60 gives us 3,892.8 newtons. Okay, so that's the components of F2. What about the components of F3? So F3, 1 in the x direction. So let's get to our angles. Let's see, this angle is 60 degrees, so this angle is 60 degrees. So our x component is adjacent to our angle. We'll use cosine. It points to the right, so it's positive. F31 is 4,495, so our x component is 2,247.5 newtons. For our y component, F31y, it points down, so it's negative. F31 times sine 60. F31 has the same magnitude as F21, so the y components have the same magnitude, except this one's negative, 3,892.8 newtons. Now, you might have guessed that the y components were going to cancel from your diagram. Had you guessed that, and if you had said the net force in the y direction would be 0 due to the symmetry, that would be acceptable. Sometimes that does take some insight to get to, so if you don't see it right off the bat, that's absolutely fine. The math will always back you up. Our last step in the problem is to do our vector addition, which means we add the x's, add the y's, and write our answer as a vector. So f net x equals f21x plus f31x, 2,247.5 newtons plus 2,247.5 newtons to give us 4,495 newtons. In the y direction, f net y equals f21y plus f31y equals 3,892.8 newtons minus 3,892.8 newtons gives us 0. Write our answer as a vector. F net equals 4,495 newtons in the x direction, which we represent by I hat. And then you might also want to draw this on your diagram. So if we had our three charges here, our F net would be here. Okay, so this is the process to follow anytime you have a set of charges. If you always follow these 4 steps the way I've gone through them, you will always get your problem correct. Here's a homework example for you to try. We have a small plastic sphere, that's the green one, that has a charge on it. It's held above a small glass bead at rest on a table. The bead has a mass of 15 milligrams and is also charged. What is the minimum distance that we have to hold the plastic sphere above the glass bead in order to get it to just lift off the problem? If you want to simulate this problem at home, maybe take a plastic comb, rub it on your hair to get it to charge up, and hold it above a few scraps of paper or tissue. You'll notice that there's some minimum distance you have to hold it to get the tissue to lift. As a hint, to get started on this problem, if you want the glass bead to just lift, you want the electric force to be at least equal to the gravity, force due to gravity. Second, a comment about the units. NC means nanocoulombs, 10 to the minus 9 coulombs. Mg means milligrams, so 10 to the minus 3 grams or 10 to the minus 6 kilograms. I'm not going to do a video, but I will post the solution.